Okay, so we're going to hold on, let me mute this first. Okay. All right. All right. I keep hearing this feedback. Okay. Testing this. Testing. Testing. Oh. Testing. Testing. Okay. That was a culprit. All right. So we're going to continue our discussion of gases, and what we'll be talking about is combining stuff that we have learned so far in this chapter with what we learned in chapter 3 with respect to stoichiometry. So basically what we'll be looking at is what is oftentimes referred to as gas stoichiometry, right? So remember, stoichiometry is that year in chemistry which deals with the quantitative relationships between substances involved in a reaction. So we're just adding gases to the mix, right? And basically we're going to use what we have learned concerning the behavior of gases and how that applies when you're doing calculations, stoichiometric calculations involving reactions, or reactions involving gases, right? So first thing we're going to talk about is this law right here, the law of combining volumes, right? And what this law says is that when gases are measured at the same temperature and pressure and they are allowed to react, the volumes of the gases, reactants, and products are in small whole number ratios, right? So this applies only to totally gaseous reactions, where all the reactants and products are gases. And what this is saying basically is that in such reactions, what you're going to find is that the ratios volume-wise between the different gases, either as reactants or products, will be small whole number ratios, provided that the temperature and the pressure of all the gases are the same, all right? So, and we can see the reason why if you think about what happens when it comes to the reaction that takes place and the mole ratios as it relates to the volume. So, for example, at a given temperature and pressure, 2.00 liters of hydrogen will react with 1.00 liters of oxygen. So the question is, why is there a 2-to-1 ratio? And the answer is very simple. Because the equation for the reaction between hydrogen and oxygen to form water is H2O. I'm sorry, not H2O. Okay, what did I do wrong here? Okay, so the reaction is H2. Okay. Right, the reaction is H2 gas plus O2 gas to give H2O gas, right? And of course, to balance this, we're going to need a 2 here and a 2 here, right? So clearly, based on the balance equation, the mole ratio between the hydrogen and the oxygen is 2-to-1, right? Well, if the temperature and pressure of all the gases are the same, that means that these coefficients would also represent the volume ratio, which would be 2-to-1 as well. But again, the restriction is that the temperature and pressure of the gases have to be the same. Once that is set, then the volume ratios will mirror the mole ratios. Here's another example. The reaction between nitrogen and hydrogen to form ammonia. And in this case, the volume ratios, or I should say the balances, we're going to need a 3 here. I'm sorry, a 3 here and a 2 here. And let me erase that the 3 that I wrote down first. So this should not be there. All right. So this would be the balance equation. And again, the volume ratios will mirror the mole ratios. In this case here, according to the information given in this sentence up here, 6 liters of hydrogen will react with 2 liters of nitrogen to form 4 liters of ammonia, right? So that's a 6:2:4 ratio. Well, 6:2:4 is the same thing as 3:1:2. And here we have the 3:1 for the nitrogen to 2 for the ammonia, right? So again, the ratio volume-wise will mirror the ratio mole-wise, all right? But again, the restriction is that the temperature and pressure of all the gases involved must be the same, right? So as stated here, we don't need to know the actual conditions for the reaction as long as the same conditions apply to all the gases. And the same conditions will be the temperature and the pressure, right? So as long as those are remaining constant, then basically we can assume that the volume ratios will be the same as the mole ratios. So based on, I thought we were going to get into the example. So this is just a pictorial illustration of the first reaction, which was H2, 2H2 gas plus O2 gas to give 2H2O gas, right? 2:1:2 ratio. And basically what this is representing is equal volumes of the different gases and show you that 2 volume units of the hydrogen here will react with 1 volume unit of the oxygen to form 2 volume units of water, right? So the volume ratios will be the same as the mole ratios. Again, the temperature and the pressure must be the same for all the gases involved. All right, so we can use that idea to answer this question. It says how many liters of oxygen are consumed for every 10.0 liters of carbon dioxide produced in the combustion of liquid pentane if all the volumes are measured at STP, right? So the first thing we need to do is what? In order to answer this question, we need to do what? We need a balance equation. So what would be the reactants in this equation? Based on the information provided. Okay, so pentane, which is a liquid, plus oxygen. And what would be the products? CO2, gas, and H2O. And then we need to balance it. So how would we go about balancing this?
H2O.
Put a 6 in front of the H2O, okay?
Reaction with the oxygen on the reactant side.
No,
3.
four.
Oh, no, you mean.
There should be a 4 in front of oxygen.
Why 4?
Because it's 2 plus 6, which is 8, and then,
So you're saying 4 here?
yeah.
What about the carbons? Because you have 5 carbons here.
So yeah, there should be a 5 in front of CO2.
Which
So
means you have to change this.
Yeah,
So
10 plus 6, 16. There should be an 8 in front of.
yeah, exactly.
O2.
So you're gonna have an 8 here to balance oxygen because 10 plus 6, 16, which balances with the 8 times 2, 16 here. Okay, so that's the first thing that you have to get out of the way. Okay, so the question is asking how many liters of oxygen are consumed for every 10.0 liters of carbon dioxide. So you're given 10.0 liters of carbon dioxide, and the question is how many liters of oxygen would be consumed. So we start out with the 10.0 liters of CO2, and then we multiply by the volume ratio between the oxygen and the carbon dioxide. So that would be 8 liters of oxygen divided by 5 liters of, right? And that will give you an answer of 16.0 liters of oxygen. And that's it. All right. So that's basically how that is done. Okay, any questions about this one? Any questions? All right, so let's move on now to a situation where the temperature and pressure are not the same, right? Now things are going to be a bit more complicated than what we just saw earlier. And in order for us to deal with these more complicated situations, more than likely you'd have to employ the ideal gas equation. So just to remind you, the ideal gas equation is, of course, PV is equal to nRT. Now, the reason why the ideal gas equation is important in this case is because it comes down to finding out what N is. So if you're given some other terms for a particular gas, the pressure, volume, and temperature, then you can use that equation to find N, and then use the mole ratio to find the N of the other substance and so on, right? So basically, just to remind you, when it comes to stoichiometric calculations, it comes down to mole ratio, right? Which means that you need to have the correct coefficients, which means that the equation must be balanced to begin with, all right? So like in this hypothetical situation, if the mole ratio is this, then to get from the moles of A to moles of B, you do the multiplication, and that's how that is done. Now, when it comes to gas stoichiometric type reaction or type questions, there may be some preliminary calculations that you'd have to do to get the moles of A. And that's where the ideal gas equation comes in. So as stated here, if A is a gas, we can find the moles of A by first using the ideal gas equation to find the moles of A. And then we do the conversion from A to B. And then depending on what the question is asking for, you may be asked to find, if not the moles of B, you may be asked to find other things like P, V, or T, right? And again, the ideal gas equation is what you use in order to do that type of work, all right? And I think the next slide is an example. Okay, so in this question, it says, in a chemical reaction using automotive airbag safety systems, nitrogen is produced by the decomposition of sodium azide. And by the way, I don't think they're using this technology anymore, but this was a technology that was used to cause the airbag to deploy when an accident happens. Basically, the sodium azide is kept in that capsule, I think, and then when the accident happens or when there's impact, it breaks, and then the impact results in this reaction taking place, and the nitrogen is the gas that fills out the airbag, all right? So that's a balanced equation for this reaction. So the question is asking, what volume of nitrogen is measured at 25 degrees Celsius and 0.980 atmospheres is produced by the decomposition of 62.5 grams of sodium azide, right? So in this particular problem, you're given 62.5 grams of sodium azide, and basically you're asked to find out the volume, presumably in liters, of nitrogen at 25 degrees Celsius. All right? So we're going to start off with the 62.5 grams of sodium azide. And the first thing I'm going to do is convert that to moles. So I'm going to have 1 mole of sodium azide above as a numerator. And then I need to calculate the molar mass of the sodium azide. So sodium, if I remember correctly, is 22.99 plus 3 times 14.41 for nitrogen. So according to my calculation, this works out to be equal to 65.02 grams of sodium azide. The next step is to look at the mole ratio between the sodium azide and the nitrogen. So that's a 3:2 mole ratio. And the way I would represent that here is that I'm going to put 3 moles of nitrogen above as the numerator and 2 moles of sodium azide below as the denominator. And then I'll work this out. So 62.5 divided by 65.02 times 3 divided by 2. And according to my calculations, and please correct me if I'm wrong, but I got 1.44 moles of nitrogen. All right. So once we do that now remember, the question is not asking for the moles of nitrogen, the question is asking for the volume in liters, right? So basically what I'll be doing next is using the ideal gas equation to solve for the volume. So V will be equal to nRT over P. N is what we just calculated here, which is the 1.44 moles times 0.0821 liters atmospheres over mole Kelvin. And then multiply by the temperature, which must be expressed in Kelvin, which would be 25 plus 273, so that would be 298 Kelvin. And then I'll divide all of that by the pressure, which is equal to 0.980 atmospheres. So let's see what I get. 1.44 times 0.0821 times 298, and then divide all of that by 0.98. And according to my calculation, I got round off to 366. So that would be 35.9. I'm sorry, 35.9. And the mole units will cancel out here and here. The Kelvin cancels out here and here. The atmosphere units cancel out here and here. So the final unit would be liters. And that's it. All right? And that's how you do that. Any questions about this? Any questions? Any questions? Okay. So let's talk about another law, Dalton's law of partial pressures. So far, in most of, if not all the cases that we have been looking at, we have been assuming that we're working with one gas and we apply the laws to that particular gas. But in this case, we're dealing with a mixture of gases, right? That's what Dalton's law is dealing with, right? And it's a rather simple law. Basically, what this law says is that the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures of the separate gases, right? So in other words, if you have n gases in a mixture, right, then the total pressure of that mixture would be P1 plus P2 plus P3 all the way to Pn, the nth gas, right? So that's basically what Dalton's law of partial pressure is all about. So now there's some important consequences of this, right? Because first, let me just say that the partial pressure, what does that term mean? Basically, that means that if you have a gas in a mixture, the partial pressure exerted by that gas would be the pressure that the gas would exert if it was by itself in the same container, right? So if we have a mixture of gases, each gas will exert their own pressure, which is represented by each of these terms right here. P1 is equal to N1 over V, P2 is equal to N2 over V, and P3 is equal to N3 over V, and so on and so forth, right? So there's some important consequences of this, which I want to discuss. So let me open this up here. So as I said before, PT is equal to P1 plus P2 plus P3 plus and so on to Pn. So therefore, for each of these, I'm going to put N1 RT over V for P1, and then for P2, N2 RT over V, and then for P3, N3 RT over V, plus and so on until you get to the nth gas, so N RT over V, right? And then what you can observe here is that you can factor out RTV, and you're going to end up with, within the parentheses, N1 plus N2 plus N3 plus and so on to Nn, right? And this here represents the sum of the moles of all the gases in a mixture, right? So we can represent that with NT. So therefore, PT can be simplified to be equal to NT RT over V, where NT is equal to N1 plus N2 plus N3 plus all the way to N. All right. So basically what this is telling you is that if you have a mixture of gases in a mixture, and you want to find the total pressure, if you know the moles of all of them, all you have to do is just add them up, multiply by RT over the volume, and that will give you the total pressure. Of course, the assumption is that it's a mixture and the gases are not reacting with each other. We're making that assumption, all right? Okay, so that's an important equation that you should keep in mind. All right, going back to the PowerPoint here. Okay, so let's look at this particular example. It says a 1 liter sample of dry air at 25 degrees contained, and it gives you the moles of the different components. And it says calculate the partial pressure of all the gases in the mixture and the total pressure of the gaseous mixture. All right, so the equation that we will use is P for each gas will be equal to the number of moles of the gas RT over V, right? So in the case of nitrogen, that would be equal to the number of moles of nitrogen, which is 0.0319 moles, times R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 298 Kelvin, which is 25 degrees Celsius. And then we divide all of that by the volume, which is 1.00 liters. And then we do that calculation. So that would be 0.0319 times 0.0821 times 298. So according to my calculation, this works out to be equal to 0.780. And the units here would be atmospheres. And basically we do the same calculation for the other gases. So in the case of oxygen, that would be equal to the moles, which is 0.000381 moles times 0.0821 liters atmospheres over mole Kelvin times the temperature, which is 298 Kelvin, all divided by, again, 1.00 liters. And let's see what that gives. 0.00038 times 0.0821 times 298. And according to my calculation, this works out to be 9.7. I'm sorry, 9. Well, let me do this again. 0.000381 times 0.0821 times 298. Okay, so that is indeed it. Okay, so 9.32 times 10 to the minus 3 atmospheres. And then for argon, that will be equal to, oh, wait a minute. I knew I did something wrong. What I just did is the calculation for argon. So let me just erase this here and put argon instead of what am I doing? So this is argon. So what I'm going to do now down here is the calculation for oxygen. So PO2 would be equal to 0.00856 moles times 0.0821 liters atmospheres over mole Kelvin times the temperature, which is 298 Kelvin, all divided by 1.00 liters. So let's see what that gives. 0.00856 times 0.0821 times 298. So in this case here, the answer is going to be 0.209 atmospheres. And then finally, in the case of carbon dioxide, PCO2, that would be equal to, okay, so it would be 0.00002 moles times 0.0821 liters atmospheres over mole Kelvin times 298 Kelvin over all over 1.00 atmospheres, liters. And let's see what that gives. 0.00002 times 0.0821 times 298 equals, okay, so according to my calculation, this works out equal to 4.89, actually 5, because it's 1/6 for the 0.0002. So let me correct that. So that would be 5 times 10 to the minus 4 atmospheres. Okay, so that's how you calculate the partial pressure of each gas, and then the question is also asking for the total pressure. And basically all you have to do is add those together. So that's 0.78 plus 9.32 times 10 to the minus 3 plus 0.209 plus 5 times 10 to the minus 4. And what do we say? 0.780 plus 9.32 times 10 to the minus 3 plus 0.209 plus 5 times 10 to the minus 4. So according to my calculation, when you add these together, you're going to get basically 1.00 atmospheres. And that's it. Okay, so that's basically how that is done. What time is it? 5 minutes. Okay, any questions about this? Any questions? Any questions? All right, this is just a pictorial representation of what we just discussed. Two gases put in the same container, the total pressure will be the sum of the individual pressures. So like in this case here, the two gases, one is hydrogen, the other one is helium. And in this case here, oh, by the way, the volumes will be the same and the temperatures are the same, right? 5 liters, 20 degrees, right? In this container, the moles would be 0.60 and the pressure exerted would be 2.9 atmospheres. In this container, the amount of helium would be 1.50 moles and the pressure would be 7.2 atmospheres. So when you combine these two, the temperature and the volume still being the same, basically to get the total pressure, you just add 7.2 to the 2.9. And this is just showing you that the moles will be combined to give you 2.10 moles, all right? So that's basically how that works. Now, there's a question here which says, what would be the total pressure if 0.90 moles of nitrogen were added to the mixture? So in other words, if you add 0.90 moles to the mixture, the total amount of gas would be, if you add 0.90 moles, right, that would give you 3.00 moles, right, which would be, well, one quick way of determining the total pressure would be looking at using the ratio of the 3.00 moles to the 2.10 moles multiplied by 10.1 atmospheres. So what does that give? 3 divided by 2.1 times 10.1. So you're gonna end up with the total pressure, in that case, being equal to, it over here, P total would be equal to 14.4 atmospheres. All right, and that's basically how that is done. All right, okay, one last thing and then we're gonna call it today. So mole fraction. This is a way of expressing, another way of expressing concentration. We are familiar with the molarity as one way, but this is another way. We can literally be applied to any mixture or any solution, but in this case, you may apply it to a mixture of gas, right? Or a mixture of gases. So here's the definition of mole fraction. The mole fraction of a gas in a mixture is equal to the number of moles of that gas divided by the sum of the number of moles of all the gases in that mixture. All right. Now, because there's a direct proportional relationship between pressure and volume, if the temperature, there's a direct proportional relationship between the moles and the pressure at a constant temperature and volume, we can express the mole fraction in terms of the pressure, right? So instead of writing it, even though this is the actual definition, right? If the temperature and volume are fixed, then basically we can express the mole fraction as equal to the pressure of that particular gas, one, divided by the total pressure of all the gases in a mixture, right? And therefore we can rearrange this to get this. So if you know what the mole fraction of the gas is, we can determine what the pressure of that gas is in the mixture by multiplying the mole fraction by the total pressure. All right. Okay, I'm going to stop there. Next class, we're going to get into this particular question. All right. So, of course, I should have your test graded by the end of this weekend. So you can look out for your test score being added in Canvas. And also, I'm going to send you your graded test. So look out for that as well.
You know.
Yes, sir.